squared term up here if you're using the 5% rule, because this plus x goes away, that minus x goes away. So it's just 2x over 2 equals this number. Okay, so we can find the x value. That's the hydrogen concentration. What do you get for the pH?
3.4.
Give me one more sig fig. 3.4. Okay. 3.40. Or Chanhi, did you mean 3.40? What? You know how he is.
Okay. Did you not get it, Sean? No, I don't get it.
You mean the letter O? Capital or lowercase o?
No, no.
We caught Chanhi. Mr. Literal. Okay, does anybody not get 3.4? 0?
It's 2 sig figs because they give us 2 sig figs, so that's what we
Yeah,
get.
you're given 2 sig figs, so you go 2 places past the decimal. Yep. Okay, so finding the pH of a buffer is just about the equilibrium. That's it. Just find the hydrogen concentration from it, from the ice table, and then solve for the pH. Next slide, we're going to take this same buffer and we're going to dump in something that attacks it. That's going to disrupt the buffer because it's going to be hydroxide ions. So here we go.
Yes, didn't we go the other way yesterday? We did this first, or this part first, and then we went?
I think we did it in the order we're doing it today. We found the pH of the non-bothered buffer and then we added something to it. I'm pretty sure that we did. So, same buffer, 2 molarity of this and this, and now 0.1 moles of sodium hydroxide is dropped in. Assume the volume doesn't change. We have 1 liter of the solution, and when there's going to be a small change in volume, but it's negligible. What is the new pH? That's when we have to use that stoichiometry step, yes.
So this is an additional.
Yep. So the hydroxide is strong base. You're throwing the hydroxide into this buffer. What is the hydroxide going to react with? Is it going to react with the acid, or is it going to react with the base? Right. It's going to react with the acid. I want you to remember this too, because as simple as it seems, when you're doing some of these problems, it's essential to remember. Bases don't react with other bases. They react with acids. Acids don't react with other acids. They react with bases. Okay? So since I'm throwing hydroxide in here, it's going to find the acid and neutralize itself, while the acid's going to neutralize the base. So it's going to be, this thing is going to kind of step up in the solution, and it's going to try to neutralize out that hydroxide ion. So it looks like this. I want you to notice the arrow. One direction. That way. Does not do any reverse tap dancing. It's going to go that way only. Why does it only go one direction? It only goes one because hydroxide is an ultra strong base. Hydroxide's job is to take hydrogen ions. It's going to take any free hydrogen ions first, because they're free. And then it's going to take, now hydroxide has a choice. It can either take ions from HNO2 or from water. Which would it rather take hydrogens from? This thing, because this gives up hydrogens easier than water does. Okay? So this thing, because it's such a strong base, as many hydroxides as there, it's going to gobble up as many hydrogens as the number of hydroxides allows. So it goes to completion until there's no hydroxides left. That's why I don't have an equilibrium arrow, it's a one direction arrow. So this is where we have to do the stoichiometry step. You identify what component of the buffer is reacting with your added substance. In this case, it's the HNO2. When the stoichiometry step is done, you should only use moles. Don't use molarity. Just use moles. Because we always use moles when we do stoichiometry.
So 2 moles plus 0.1.
We got 2.0 moles. We got 0.1 moles. Now, this is something I didn't do yesterday, but I'm going to do it today. For the NO2, this conjugate base, yesterday I was just calling that 0 because it was 0 caused by this reaction. But today I didn't like it so much yesterday calling it 0. So I'm going to say the amount of NO2 that's already there is still 2 moles. Not still, but that amount of NO2 negative was there at the beginning. It's there as the conjugate acid attacks that hydroxide.
Yeah. Why should we use molarity?
Why should we not use molarity? There will be times when the volumes change, like you'll be adding some solution to another solution. It's best to use moles.
Okay.
Because of the dilution part of it, use moles. So, because it's a one direction arrow, these are going to go to completion based on whichever the limiting reagent is, which is the hydroxide. So that's going to go to 0. And since that's all that got used up, this goes down to 1.9. When these go down, this goes up. Since it was by 0.1, it's going to go up to 2.1 moles. You see what happened? Who said no? You? You say no because you're being a bad guy, or you really don't? You're being a bad guy.
Wait, so don't you have to balance the equation, or will it always be balanced?
They'll always react in the 1-to-1.
So first this reaction occurs, and then it tries to establish its equilibrium back.
Now it's going to get back to equilibrium. Yep. So the question is, what is the pH? This amount of the acid and conjugate base have now been thrown off. Now we have a little bit less acid and a little bit more base. Okay, fine. We now can go back to the equilibrium of this acid and water, because you have a concentration of acid here, concentration of base here, and find what the new pH is. And that's what we have to do. Now, down here we have the ice table, so we're going to go back to molarity. We had moles here. Since it was 1 liter, then the moles divided by 1 liter is just the same as the molarity. So the HNO2 has now gone down to 1.9 molarity, because some of it got used up. The NO2 negative goes up to 2.1 molarity. It's still almost 2 molar, but it's not quite. So what is the new pH? Well, you still have the same Ka value. It's right there, 4 times 10 to the negative 4th.
So would we add do plus x and plus x on the right
It's
side?
got to shift to the right because you have a term that's 0, and it can't be 0 at equilibrium. So it's going to be minus x, plus x, and plus x. So that times that over that equals 4 times 10 to the negative 4th. What is x and what is the pH?
What was the pH before?
3.40. And when you get an answer, ask yourself, okay, is this reasonable? You know that the pH is going to change some. The thing about a buffer, though, is it doesn't change much. Mina, does your answer seem reasonable?
Yeah. Yeah.
What'd you get?
3.44.
3.44. Can I get a witness?
Yeah.
Are we together on that? So the pH went up. It was 3.40 before this hydroxide was thrown in there. It just creeps up a little tiny bit. That's what's good about a buffer. If this was not buffered, you drop a tenth of a mole of sodium hydroxide in there, the pH is going to jump up to about 13 or 14. But because there was buffered, the pH goes up by 4/100ths of a pH unit. That's quite a difference. That's what buffers are good for. Yes.
So the more HNO2 and the more NaNO2 we put in the solution, the less it goes up.
That's right. That's right. Yep. Okay, now we walked through this one together. What I'm going to ask you to do now is try a problem very similar to this one. In fact, we're going to use the same buffer system. It's going to be 2 molar HNO2 and NO2 negative, and then 1 liter. So it's the same exact buffer solution. But this time, what is the pH if 0.5 moles of HCl are added? What is the pH of 0.5 moles of HCl are added? that is the biggest hump to get over in this chapter is what equation do I write? What reaction is going on? So yeah, that's not bad to ask that. That's really what we have to deal with right now. What's reacting with what? Now, let's answer that. You've got HCl, strong acid, so you've got this flood of hydrogen ions. What are the hydrogen ions going to react with? The acid or the base? It's going to react with the base. Yep. So I'm going to just give you a boost. H plus, there's our strong acid. Plus, it reacts with the base. One direction. By the way, I'm not much of a fan, so I don't know if you keep hearing me say that, and you think, oh, you must love One Direction. It's the boy band. Okay. You can think what you want. That's not really true. And now, what's made? Well, there's not many choices of what can be made. It's just these two are going to combine into HNO2.
So wait, the CL's is not good.
Spectator. It's not doing anything.
That's
Yep.
what confused me.
Yep. So we have to do the stoichiometry first, then apply the equilibrium to determine what the pH is. Do you smell something?
Yeah.
It smells like burning wax. I've been smelling it
Wonder
for
why.
like 5 minutes. It's really funny.
Yeah. And I know he's not doing anything with it next door. I don't think he is.
So are we adding 0.5 molar to, 0.5 moles? Or
Moles, not molarity, moles.
moles to the original solution, or
The original one, yeah, not the one after it's been messed with. Okay, good. So you have the new numbers of moles, right? You remember the ammonia and ammonium example we did at the beginning? How it didn't matter which you used? Use an equilibrium of acid and base. Doesn't matter which one you put as a reactant.
there's no other equation. So now, you know, what is the K equals
4
K,
times 10 to the negative 4.
That's just our solution. So now you do is look at that. You have HNO2, you have H plus HNO2. And K, okay, so K, right? K always is with respect to the acid. So K is that equation.
Well, this one's attacking. That's why it's.
Right, so, no, so that's done, right? So now you do the later the K value to write the Ka equation.
Yeah, I know that, but what's
Which is HNO2 plus HNO2 makes H2NO2.
Oh, it's the same thing?
Yeah, because it's Ka. Ka is how the acid is made.
How do you add it after that you become the same thing?
Yeah, check your answer. We have added acid to it, so what should the pH be doing? It was 3.40 before we messed with it. Then we added a healthy amount of acid to it. Did you get it? Keita, did you get it?
Wait, there was already.
Be confident, you guys.
Are you doing? Oh yeah,
If it seems right, it's going to be right. Yeah, so you know you did it right. A little bit lower, right? It doesn't go down to like 0.
I mean, it's still a huge amount compared to the over 8. Oh, I see why. Because we had 0.1 moles over here, we had 0.5.
Right. That's right. So it changes by more this time.
Is it 3.18?
Wait, what?
1.8. It's got to go down because we had strong acid. Now our buffer has less base and more acid, so it's going to go more to the acidic side.